Welcome to this web lecture on the Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm is an algorithm to solve the maximum flow problem. So, just to recap, what we're doing, we were solving the problem of TUI Airlines, an airline that operates a network of direct flights in Europe, allowing passengers to change over between flights. They had an issue because their direct flight from Rome to Amsterdam was cancelled and passengers must be assigned to different flights. And what we want to do is we want to assign as many passengers as possible to other flights. So what we need an algorithm. An algorithm is a systematic procedure that produces, in a finite number of steps, the answer to a question or the solution to a problem, which means that an algorithm is problem-based, is an unambiguous set of instructions, and terminates eventually, so we don't want to run until the end of time. So the algorithm that we're looking into is the Ford-Fulkerson algorithm, named after these two gentlemen. And the Ford-Fulkerson algorithm works on the maximum flow problem, and it provably returns the maximal flow in pseudo-polynomial time if the graph is acyclic and has integer capacities. So what does this mean for us? This means, first of all, this is actually not a heuristic, which is a huge difference to most other algorithms that we've been looking at throughout this course. And then we have a few restrictions that we won't focus on too much during this course. So what does this algorithm do? So in the first step, we set all flows to 0. So we say xij equals to 0 for all I and j. Secondly, we determine an augmenting path from the source to the sink with strictly positive residual capacity and determines minimum residual capacity m. And if none exists, so if we cannot find a path, then we can terminate and return the maximum flow. If we find one, so if we find a path with a positive m, then we increase flow along this augmenting path, and then we repeat from step 2. So let's look at a very simple example, and then we also see some of the special cases that can happen with this algorithm. So the first step that we're doing is we're assigning 0 flow to all arcs in this network. So we say, for instance, from S, which is the source, to node 1, we currently have a flow of 1 out of a capacity of 3. So then the second step is we're determining a path, and it doesn't need to be the best path at this point, which has still residual capacity, and we call this the augmenting path. In this case, the augmenting path is from S to 1 to 2 to T. And we see that here the residual capacity is 1 because we have 3 arcs with residual capacities of 3, of 1, and of 3. But obviously we cannot increase the flow by 3 because that would be way too much from 1 to 2. So we're going to increase it by exactly 1, and this is step 3. So now our total flow is 1, and we can start again with step 2, which is finding an augmenting path. And in this case, the augmenting path is from S to 2 to T. And here we have a residual capacity of 2, because we can still increase the flow from 2 to T by at most 2, because we already have 1, but we could have at most 3. For instance, passengers, if we look at the case of TUI Airlines. So this is what we're doing. We're getting a flow of 3. Now it gets slightly difficult, but what we can still do is we can still send people from S to 2 to 1 to T. That is not fairly obvious, and this is also the one tricky part of this algorithm. We can send people from 2 to 1, and this means more or less deciding not to send people. So what we're doing is we're determining this augmenting path, and then we're increasing the flow by 1, but actually we're decreasing it by 1 from 1 to 2. So this is what happens here, which means that all of a sudden we have 3 people going from S to 2, and we have 1 person going from 1 to T. And if you look at this solution, you still see we still have flow conservation, and we also increased our total flow, which is because we traversed this one arc in the opposite direction. And now what we're doing is now we're continuing with step 2. We find yet another path. We see from S to 1 to 2, we can still increase the flow. We can increase the flow by at most 2. So that is because we have a residual capacity of 2 from S to 1, but we have a residual capacity of 3 from 1 to t. So we increase it, and now we check again. We see, okay, we cannot find another path. We cannot send anything from S to 2 to t, because from 2 to t we're at capacity. We cannot send anything from S to 2 to 1 to t, because we cannot decrease it anymore from 1 to 2. We can also not send anything from S to 1 to 2 to t, because we're at capacity between S and 1 as well. So we've definitely found the optimal solution, and we can return the solution with a maximum flow of 6. So this was the Ford-Fulkerson algorithm, and what I would like you to take away from this web lecture is, first of all, what an algorithm is. Secondly, we've looked at this small example of the Ford-Fulkerson algorithm. What I would like you to do as a homework is work on the larger example, which is the TUI Airlines, the full network. And what we're going to look into in the next web lecture is the assignment problem, which is a variation of the maximum flow problem / can be cast into the maximum flow problem, which means that you can also use the Ford-Fulkerson algorithm here.